We looked into forward in time centered in space scheme for solving the advection equation, and we saw that some of the inherent limitations of using such schemes for practical problem where we quickly run into instability and our time stepping should be very small, and this puts a lot of stress on computational requirements. So we said we will talk about a cure for such instability issues using the lax method, and that's what we will going to look into this particular exercise. Before going into the lax method, we will spend a little bit time in the forward in time centered in space scheme, and if that is essentially given by this particular equation what we have in the forward in time centered in space scheme, C delta t by 2 delta x, the value should be much lower than 0.5. When we are going closer and closer to 0.5, we run into some instability issues. So in other words, R equal to C delta t by 2 delta x, which is half of the CFL requirement. Remember, this term is a CFL term, and since it's half of the CFL term, we have to be in the range that is, and as and when we are going closer and closer to 0.5, we run into instability issues. In fact, we have to be very low compared to 0.5. So now with this background, we are going to go into the lax method. So the lax method is a clever way of fixing this problem. So in other words, what we are going to do is, instead of having the value u of n comma j, we are going to substitute average of the values. In the average of the values, what we are doing is we are taking the value at time step j, but n plus 1 and n minus 1. So remember, our stencil is going to look like this. So this is time step j, j plus 1, j minus 1, and this is n, n plus 1 and n minus 1. So we are going to compute the value at n comma j plus 1. So this is the value that we are interested in. So initially, in the case of the forward in time centered in space scheme, what we did is we used the value at time step n comma j. So n comma j, so I am going to mark them in green. So we use this value, and then we use the value at time step j n plus 1, we use this value, and then we use n minus 1 comma j. So we use this value to compute the value at, let's say, at this point. Now what we are going to do is, instead of taking this value at time step n comma j, we are going to take the value at j, but we are going to take the value that is average of these two values, n minus 1 and n plus 1, and that's what this equation is about. So what you see is we don't take the value at n. So that way the advection equation itself becomes as follows. Remember, in the previous case you had n comma j, instead of n comma j I am going to use this value, and then the equation will become like this. So once we have that, we are able to somehow improve the quality of the scheme, and it essentially goes to the CFL condition which we talked about, which is due to Courant, Friedrich and Levy, and this condition is pretty much going to be there in every scheme that we are going to do, and some schemes, at least in the explicit methods, implicit methods we are not worried about CFL condition, but for almost every explicit method, CFL condition is going to be very hard condition, and with this lax method we are able to improve the quality of the solution for a larger R value, and that's what we are going to see in this particular example. So let's go into the MATLAB program itself. So before going into the main program of the lax method, I am going to one more time look into the advection equation using the explicit method, which we did in the previous modules. So remember that the R value is going to be strictly lower than 0.5, and in fact we have to have R value that is very low compared to 0.5, and let's run the program one more time for this explicit method, and we will see how the solution looked, how it is going to improve using lax method. So remember our R value when it is equal to 0.3, and when you are running the equation we are running into a huge instability issue. The value of the amplitude is going to 3 into 10 power 5, which is a very large value. So in order to solve for this issue, remember that we have to go very low in the time stepping. So R value should be equal to much lower. So R value typically is in the range of 0.0001. Once you do that, you start to see that the solution is coming closer and closer to the expected solution. So now you are able to see the value is coming closer to the expected solution, where the square wave is being replicated by the numerical method, and the expected result is correct, but of course we have to go very low in R value. So as we said, we are going to change this situation and use a different method using the lax method. So let's introduce the lax method itself in this particular MATLAB code. As before, it's a step wave test function, and what we are doing is we are trying to use the value instead of explicit method. We computed the value using u of I comma k. In the lax method we are going to use 0.5 u of I plus 1 of k and plus I minus 1 of k, and we are taking the average of those. Let's try running the program for various values of r's. So let's say we are going from, so now I am going to keep r value is equal to 0.3. I am going to run using the lax method. So I am running it now, and we will see the value is replicating even for r equal to 0.3. The value is coming closer to the initial condition. As I said, the different colors are for different time steps, and the initial condition is given by this particular line here, the purple line, and as the time step goes forward, the solution itself is propagating in the forward direction. That's what we are expecting, and that's how it should be. And now we'll see what happens when we go r equal to 0.5. We see that still the solution is within the expected range. Of course, there is kind of some errors that are coming in the square wave function, and these are due to the numerical errors of the scheme itself. It's still first order and the second order in time and space respectively, but for that order this is a very good replication of the differential equation. And as you can see, we are able to run the program for r that is even higher than 0.5. So when we run for values that are higher than 0.5, we are still able to run the program. So what we have demonstrated using this particular lax method is, instead of taking the value at u of n comma j, when we take the average at a broader stencil, we are able to improve the stability issue. The program is still not accurate, but still it is stable enough for us to run the program to see some simulation results. Obviously there are some numerical issues that comes because of the first order in time and second order in space, and of course this is something that we should definitely improve if we wanted to do any numerical problem solving using these methods. But what we wanted to demonstrate using these examples is there is definitely some numerical issue coming from the forward in time centered in space scheme. We can improve that numerical stability issue or the numerical instability of the method by taking the average. That's what we have done using this example. So what you are seeing here is the solution itself is moving in the direction. This is a 2D image of this particular solution, and you are seeing that there is an advection that is happening, and the initial step input has to go through the entire domain and it will propagate, and that's what is the idea of the advection equation. We can solve the instability issue that is inherent in the forward in time centered in space scheme using some clever way of averaging the field variables at different points in space, and that is what the lax method has shown us. So it enables us to run the simulation for even bigger values of R. And now I would like to leave this particular module with a question in mind, and that is also something I wanted you to try it out, is the staggered leapfrog technique. So remember, in the standard advection equation we did forward in time centered in space. So we did simple forward differencing in the time variable, and we did centered in space in the spatial variable. So what if we do both the space and time in centered manner, and that is what the leapfrogging method is going to be about. And the standard equation for that is going to be of this form, and you can basically do the centered differencing both on the left hand side and on the right hand side. Remember that in a centered scheme you will have the value u of n comma j plus 1 minus u of n comma j minus 1 divided by 2 delta t is equal to minus of c u n plus 1 comma j minus u n minus 1 comma j divided by 2 delta x, and this 2 and 2 gets cancelled, and that is why we have only delta t in the equation. That is what you see in this particular equation. We call this as centered in time and centered in space, CTCS. It is nothing but the staggered leapfrogging technique. I would like to encourage you to do the same MATLAB program for this particular scheme as well. Of course, we will provide you with the MATLAB code for explicit method using the forward in time centered in space and also the lax method. So once you can have those codes, you can basically rearrange the terms and do accordingly for the staggered scheme, and you will notice that the scheme is also having certain properties for stability, and which is good in some sense for you to try it out yourself before I say anything about it. So that will be a exercise problem for people to look into it during the course of the week. So now, with that being said, we will come to a stop at this point, and then we will take it forward in the next module. Thank you.